Hi there and welcome again to Cambridge Advanced Level Mathematics. Remember, in our last video, we were dealing with the first order differential equation, which of course we had taken from our past examination questions. I thought I should just follow up today with a simple question, probably not from an examination question, but I just pulled it off a textbook. And the question is up on the board here, and it reads as follows. Sketch the family. Look, I have underlined the word family of curves. Sketch the family of curves given by the differential equation dy dx is equal to 4x, and determine the equation of one of the curves which passes through the point 2, 3. Let's read it again so that we can understand it better. Sketch the family of curves given by the differential equation dy dx is equal to 4x, and determine the equation of one of the curves which passes through the point 2, 3. Now, let's rewrite our differential equation again this side and say, it says dy dx is equal to 4x. This, by the way, is called a differential equation because it is an equation which contains differential coefficients. And again, it is called a first order differential equation because the highest differential here, the highest derivative here is the first derivative. If it was the 2y dx squared, it would be called a second order differential equation. And so here we do have a first order differential equation. It's one of the simplest differential equations you can ever get. Now, what do we do? First of all, because our aim is to solve the differential equation, and solving the differential equation is getting an expression that an equation that expresses y directly or maybe indirectly in terms of x, and get rid of the differential coefficients. So what do? Let's integrate both sides with respect to x. So this implies, I'll put my integral sign there. Let me put my dy dx there, and I will put it in bracket. We are integrating with respect to x. So there we are. And treating both sides the same. So I'll have my integral sign there, my 4x here, and I'll put it in brackets, integrating with respect to x. Nothing has been violated. I am integrating both sides with respect to x on both sides. Right. Inside this bracket here, what do we get when we integrate dy dx? Remember, when we have y and we differentiate it, we get dy dx. So since integration is the reverse of differentiation, if I try to integrate this with respect to x, I must get back my y. Because if I differentiate this with respect to x, I get this. Okay? So once you get that, you know that here on the left-hand side, integrating the y dx with respect to x, we will get a y. Okay? What happens when we integrate with respect to x? Our 4x, power rule in motion, x squared divided by 2, that gives us 2x squared. So this is equal to 2x squared. Remember the power rule, it says raise the power by 1 and divide by the new power. So the new power is 2, dividing 4, that gives us a 2. But we need a constant of integration. Right. So that is now the solution to the differential equation dy dx is equal to 4x. We have solved the differential equation. Now, if we were to plot this on an xy plane like this, okay, this is our xy plane. This is the y-axis there. When c is 0, We know that this will be the graph of y is equal to 2x squared. It passes through the point 0. It will have perhaps a shape like this. I hope I get my shapes right. So this would be the one where y is equal to 2x squared, with c is equal to 0. If c is equal to 1, this whole thing would be lifted up 1 unit, and it would be, let's try and use another color, it would be this would be the graph of y is equal to 2x squared plus 1. C is equal to 1. When C is equal to 2, let me see if I can get a blue here. Yes. When C is equal to 2, we would then get the graph of, this would be lifted up from 0 2 units. So it will be something like this. This would be the graph of y is equal to 2x squared plus 2. I hope I'm not getting things mixed up there. Supposing x is equal to minus 1, then this whole graph would be pushed down 1 unit, and it would be, see if we can get a green somewhere. Yeah, there is a green. Okay, so this would look like, okay, that then would be the graph of y is equal to 2x squared minus 1. C is equal to minus 1. So let's just write here, C is equal to minus 1. Here, this represents our C is equal to 0. This represents our C is equal to 1. This represents our C is equal to 2. This then is what is called the family of curves. The solution to the differential equation gives you a family of curves. Until we are given additional information, we cannot actually plot a particular graph representing the solution. Now, when we are given additional information such as this one, which are called initial conditions, the initial conditions are that when x is 2, when x is 2, y is equal to 3. So if we then substitute into our equation, remember our equation is here, so let's substitute the values. We have y is equal to 3, and our x will be 2, so that will be 2 multiplied by 2 squared, which is 4, plus c. So that gives us 3 is equal to 8, 2 times 4, plus c. So what is c? C is equal to minus 5. Okay, so c is equal to minus 5. So the particular graph now that would represent this particular equation now, where we can write it as, so now since we now know c is equal to minus 5, we can write the equation now is y is equal to 2x squared minus 5, because c is minus 5. This is now called a particular solution because it results from us using additional information supplied. So where does it plot? I'll plot it in red here. So this is where we said it was minus 1. So minus 5 would be down here somewhere, isn't it? So that would, not a pretty looking graph though, but I hope you get the point that now this is the one that represents c is equal to minus 5. That is a particular solution of the differential equations. All these represent the family of curves representing the general solution of the curve when c is an arbitrary constant that we know. And until we are given additional information, we don't know C, it will be just like that. When we get additional information, in other words, boundary conditions, then we can now find a particular solution, which in this case is y is equal to 2x squared minus 5. And we can plot a particular graph on the xy plane, just like that. That is, as I said, one of the simplest differential equations that you can ever get. We will proceed in the next videos to greater complexity until eventually we get to solving second order differential equations. I did talk of complexity, but it does not mean they are difficult, they are impossible. It just means they are a little bit involved, but they are doable.